Hi everybody. This is what you're going to do with your plates when you come back to lab. So last week you plated your bacteria on the 5 TSA plates or the 5 PIA plates, both for the A half and the B half, and then you taped your plates shut and put them in the drawer. This week you're going to come back. The lab will smell terrible. I am sorry about that, but it's unavoidable. Bacteria are smelly. And you will locate what is called your countable plate, and you will count the number of bacteria that have grown there, and that is how we will determine the number of bacteria that were in the soil to start with. So you'll get out your 5 plates for each stack. So I didn't want to use any of your plates, and I didn't make my own set of plates. So for the video, I'm just using a picture of plates, but hopefully it'll be enough to get you the idea. So you'll get out your set of 5 plates, like your 5 TSA plates or your 5 PIA plates, and you'll lay them out on your table. And we are going to look for the countable plate is defined as the plate that has between 20 and 200 colonies. So below 20 colonies, then there aren't enough for you to get the same number with every time that you suck up 100 microliters. So below 20 gives you what's called sampling bias, and it will introduce error into your count. Above 200 colonies, it's really hard for you to be accurate as you are counting. You might double count one, you might not count one, and so that will also introduce error. So between 20 and 200 colonies on the plate is what we're going for. That is called the countable plate, and that will give you the most reliable number. Hopefully, since you've done the tenfold dilutions, you should only have one plate that falls within that 20 to 200 range. You might have two, but try to pick the one. If you do have two, let's say that you have like 20 and 200 or 18 and 180 or something. Pick the one that is closest to the middle of the range. Okay, so this is my picture. These are my 5 plates I have. Pretty confident that these two here are way over 200. I'm not going to count those. I think that this one is my countable plate, so I'm going to start counting it. I think that these two are probably going to be below 20. This one could be on the line. I'm not sure. But I think that this one is going to be more in the middle of the 20 to 200 range. So that's the one that I'm going to count. So let me zoom in on that plate, and I can show you guys how to count it. Okay, so you'll count with your Sharpie. I'm actually going to X out because I accidentally dotted on the plate there. So the way that you do it is you get your Sharpie out of your second drawer and you dot the colonies as you count them. This helps you to keep track of where you are. So the bacterial colonies are going to be round. They will be mostly white. They could be other colors. If you find 2 circles smashed together, like these two are obviously 2 different ones because they're 2 different colors. But if you look at this orange one right here, it's got like one at the top and then one at the bottom. And then I'm even thinking a third little tiny one down there. So basically, you're counting each individual circle of bacteria, whether it's an independent circle or 2 circles mashed together, you count as 2. So you count each circle. You'll also count the ones along the edge. If you get some long stringy ones, which you might get, then try to count the middle of the stringy disaster and assume that all of the strings are connected to that. Okay, so here we go. We're ready to start counting. I'm sorry, you just have to wait with me while I'm counting. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 2, 3, 4, 5, 6, 7, 8, 9, 40, 41, 42. I think this is all one, so I'm going to call that 43, 44, 45, 46. Sometimes on the edge they'll get real spread out, but so even this one is kind of a teardrop shape. I'm still going to count it as one. That was 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 2, 3, 4, 5, 6, 7, 8, 9, 70, 1, 2. So it's a little bit tricky with the picture, but I think that I have counted 72 colonies. You can write right on your plate when you get it. And then I also am going to need to know which dilution this is. So I don't know if you guys can see. You can. But this is the 1 times 10 to the minus 4 dilution. So now I've got my number of colonies and my dilution. I am ready to do the calculations. So this video is both to be watched for how to do the lab, which is this bit, and for how to do the pre-lab, which is entirely calculations. So let's start on that. Let me get another sheet of paper here. Zoom out a little bit to make sure that I don't write off the edge of the paper, because that would be no good. All right, so we counted 72 colonies, and it was on our 1 times 10 to the minus 4 plate. The other information that we need is how many milliliters of liquid we put on the plate. So good news for you guys, hopefully, good news. You should have put the same amount on all of your plates. You should have put 100 microliters, which if we divide that by 1,000, because there's 1,000 microliters in 1 mil, gives us 0.1 milliliters. Scoot the decimal over 3 places to divide by 1,000. Oops, and I wrote off the edge of the screen anyway. I can't believe it. Okay, now I'm definitely ready. So we have our number of colonies, our dilution, and our volume plated. So those are the 3 pieces of information that you need in order to do this calculation. So the reason that we care about colonies is, you guys remember last week when you spread your bacteria out on your plate, and I told you it was important to get them really spread out and not let them clump up. That's because when you spread out the bacteria, each individual bacterial cell ended up in a different place. And then it divided in half, and then in half, and then in half, and then in half, until it made essentially like a little mound of bacteria that were exactly the same as itself. And so this is what we counted today. This is a bacterial colony. The original bacterium that started the colony, we can't really see it by itself. All we can see is the colony. But we call the original bacterium the colony-forming unit. So we counted 72 colonies, and that means that on that plate there were 72 colony-forming units, which we abbreviate as CFU. So that's the same as 72 CFU. Okay. So what you do is you take your number of colony-forming units. What we're going to try to get is colony-forming units per gram of soil if we started with a solid sample as we did today, or there is one in your homework that is in lake water. So for that, it's going to be colony-forming units per milliliter of lake water. So it's really important for you to read where your original sample came from. So to start, we're going to write down our number of colony-forming units. So then we put it over the volume plated must be in milliliters. So then we're going to put over 0.1 milliliters plated. Okay. So this next part is a little bit tricky. So I'm going to try to explain it to you, and I'm really hoping that it comes across. All right. So we've got our undiluted is like your soil that you went and picked up from your plot. And then you made the -1 dilution, the -2 dilution, the -3 dilution, and the -4 dilution. Okay? So this is 1/10 of the original, 1/100th of the original, 1/1000th of the original, 1/10,000th of the original. Hopefully everybody is good with this from last week. So we counted in my little picture, the countable plate that I had was the 1 times 10 to the -4 plate. But no one at all cares actually how many bacteria are in here. What everyone wants to know is how many bacteria are in your original soil sample. And so what we have to do is we have to take the number that we counted divided by the volume on the plate and multiply by a positive exponent version of the dilution, which is somewhat confusingly called the dilution factor. So since this is the 1/1000, sorry about that, I got into a glitch and I had to restart. Okay, so here's where we were. So we have counted 72 colony forming units on our 1 × 10⁻⁴ plate, and those 72 colony forming units were in a volume of 0.1 milliliters that we put on the plate. So what I was saying was, no one cares actually how many bacteria are in the 1 × 10⁻⁴. What everybody wants to know is how many bacteria are in the undiluted soil sample. And so since we know that the 1 × 10⁻⁴ is 1/10,000th of the original, then we can figure out how many bacteria were in the original by multiplying the number that we have counted by 10,000, or by 1 × 10⁻⁴. And so we're going to take this number that we counted divided by the volume plated and multiply it by the dilution factor, which is the positive version of the dilution. So if I counted the -4 plate, I'm going to multiply by 10⁴. If I counted the -6 plate, I'm going to multiply by 10⁶. And so the dilution factor is the positive exponent version of the dilution that you counted. Okay, so then from this we have 72 dividing by 1/10 is the same as multiplying by 10. And so we have 72 times 10 colony forming units. We still leave milliliters on the bottom. The units don't get moved. And then we have times 10⁴. Okay, do you guys remember last week when we did exponents? All right, so I've got 720 colony forming units per mil times 10⁴. Great. So what we can do with the scientific notation and the exponents is 720 is the same as 7.2 times 10⁻². So you guys remember 10⁻² is 100, or moving the decimal point 2 places. And so I can take my decimal point and move it 1 here, 2 here, and then I have 7.2 times 10⁻². This is important because then I can rewrite my 720 as 7.2 times 10⁻² colony forming units per mil times 10⁴. Okay, so what I can now do, since I've got 10⁻² multiplied by 10⁴, the way that you handle that is you actually, if you have two numbers that are multiplied, you actually add the exponents together. And so this becomes 7.2 times 10⁻² + 4 colony forming units per milliliter, or 7.2 times 10⁶ colony forming units per milliliter. I can leave it like this, or I can write out 7 to 1, 2, 3, 4, 5 colony forming units per milliliter. Okay, so we are done with the algebra part. We have one little thing left to do, and the problem is, of course, oopsie, besides my being off the bottom of the screen, the other problem is that we are interested in the number of bacteria in the soil sample, and soil is a solid. And so what we can do with this is we use this somewhat handy convenience that is 1 gram of water. The amount of water that weighs 1 gram is equal to 1 milliliter. And since we had suspended our soil in water, then we can just say that this is the same as, I'm going to rewrite it with the 10⁶, because all these zeros just, I'm worried about losing 1 or adding 1 or something. So I'm going to rewrite this as 7.2 times 10⁶ colony forming units per gram of soil. I'm going to box it so everyone knows that it's my actual answer. Ta-da! There you have it. So that's what you do. Let me get a different color and just rewrite the tips for you fast. Getting a different color is actually more tricky than I expected. We'll go with this super festive magenta shade. All right, so you count has to be, remember, between 20 and 200 is your countable plate. So you're going to count your number of colony forming units. You're then going to divide that by the volume plated in milliliters. So for your homework, you'll have to read the problem and see what the volume plated in milliliters is. For the lab, it was always 100 microliters, so 0.1 milliliters. All right, so you take your number of colony forming units counted, divided by your milliliters plated, and multiplied by the dilution factor, which is secretly the positive exponent of the dilution. Okay, sorry, I wrote off the edge. Then you remember that if you get two numbers that are like 10 to the 2 and 10 to the 4, then you add the exponents when multiplying with the same base. So I couldn't say like 2 to the second times 10 to the 4th because that's a 2 and that's a 10. But if I had 2 to the second times 2 to the 4th, then I can do add the exponents, and that gives me 2 to the 6th. So as long, oops, forgot the word base. As long as you have the same base, you can add the exponents. And then the last thing, do not forget this, is make sure that your units make sense. So if you're supposed to be doing how many bacteria are in the soil, do not write milliliters. Be sure that you write grams of soil. But on the other hand, if the problem asks you for how many bacteria are in a water sample, you will need to write milliliters. So the last step is to make sure that your units make sense.